good morning, everyone. I'm super excited here to talk about this very fascinating field of theoretic physics and aesthetic correspondence. And before I start, I assume that not every one of you has heard about this term before, so I'll give you a brief definition of what it actually means. So in short, this correspondence is actually proposed by Anderson in his groundbreaking paper in 1997, where he said that type 2b superstring theory on any space-time is actually equivalent to a four-dimensional square muse in acoustic space-time with H group SUN. Okay, at the moment you probably feel really bewildered of all these terms. What is actually type 2b superstring? What is square muse? What is HS5? Given that, I'll make my mission to explain these in the following part of my talk. This talk will be divided into two halves. In the first half, what about this? In the first half, I'll just give you the very brief introduction of the foundations I need to have to understand this correspondence. All those unfamiliar terms you see in the definition will be explained in some detail here. And after laying down the foundation, the second half of my talk will be about the motivations. That is why Marcel proposed this correspondence of these two seemingly different theory, and then naturally the segues to holographic principle. Finally, I'll give you some evidence why this is actually true, even though it's not mathematically proven. Now we turn to the first half. In the first half of the first half, right, I just talk about the conformal field theory. All right. Just pertain to the point that my click there. Okay, so conformal field theory is actually a quantum field theory with conformal invariance. Conformal field theory is a quantum field theory with conformal invariance, which is actually saying that this theory is invariant under conformal transformation. So I'll start by defining this conformal transformation. So mathematically speaking, after a conformal transformation, the metric of the theory will change only up to a proportionality, which is only dependent on its coordinate. So you divide both sides of the equation by dx alpha, dx beta, get this one. So quite naturally, you identify Poincare transformation, which we have learned for quite a long time is a special case of conformal transformation, equivalent to lambda d equal to 1. And although it has a special property of angle preserve, actually conformal means angle preserve after conformal transformation, all angles before will be the same after this transformation. It's quite easy to prove actually. Right. And you know how to calculate angles, the norm, the inner product divided by the norm of those two vectors. And in the denominator, if you use this lambda, in the denominator, if you use this lambda, the both cancels, the angle will be the same. And we want to find the generators of this conformal transformation, always want to do so. And recall, to do so, we have to consider infinitesimal transformation like what we did in quantum field theory. So consider such infinitesimal transformation and plug it back in this equation, we get this one. And then taking derivative with respect to coordinates, we get this, the first term, and changing the orders of the derivatives, we'll naturally get this one here. I want to go through all the details here because we have limited time. And finally, arrive at this. This is an equation that F must satisfy to be a conformal transformation. So consider different d, that is a dimension. For one dimension, this is a trivial case because d equals 1 will give you f, taking whatever values you have will give you conformal transformation. And it's quite straightforward actually. In d equals 1 dimensions, you don't have any concepts of angles. After any sort of transformation we perform, that angle will remain the same. And the d equals 2, this is a special case, most interesting of all. It gives you the Rosberg algebra, which contains infinite number of generators. This will be widely talked about in string theory because the string worksheet is actually two-dimensional space-time characterized by two parameters, tau and sigma. So it's that. And in this talk, we'll focus on the d greater than 3 case. Because partial square f should be equal to 0, this gives you f must contain the highest terms up to the linear to x. And then plugging back in this term gives you the general form of the infinitesimal parameters. Then, because the linear term should be equal on both sides of the equation, so this gives you some sort of constraint. You have to match the coefficients for both the linear terms and the conjective terms. Then you can solve the equations very easily, and then you get the expression for the infinitesimal transformation. Then identifying different parts of it gives us 4 times of conformal transformation, translation and rotation, which actually forms a Poincare transformation, as you probably know from this course. And then give you 2 new dilation and special conformal transformation. This is from the alpha. This is dilation. This is special transformation. So these 4 actually are when we talk about conformal field theory. These are the 4 types of conformal transformation. And by plugging in the definition of generators of a transformation, we get the specific representation in specific form of these generators in differentiation operator representation. Then by using the standardized quantum mechanical commutators, which is xp, commutator of xp equals I, we get this conformal algebra. So this is quite straightforward, you can work it out. And you can see this dpk, dpm, actually form a subgroup of conformal group, which means they're closed in themselves. And also these 2, p and k, transform as vectors under the action of m. That those Lorentz vectors, which actually brings out. And this is general Lorentz algebra, so it's very straightforward. And by redefine those generators by re-linearizing them, we actually get to see these generators satisfy the Lorentz algebra, which means that conformal dimensional CFT is actually has SO2D as a conformal group. Because as you know, that Lorentz group in 4-dimensional Minkowski space has SO1-3 as its symmetry group. So it's actually a generalization of that, which will be important in motivating this correspondence later. And conformal field theory actually is stronger than Poincare symmetry. So it imposes some constraints on those physical observables like 2-point correlators or n-point correlators, which we have to calculate the S matrix in conformal field theory, a concept which doesn't exist here, but still. After a dilation here, this operator will change by a factor lambda to the power of k. This is like an assumption because it's only dependent on lambda, okay? And then it has to take this form because of this. Because this series is conformal invariance, which means it must be translation and rotation invariant, but this can only be the function of the relative distance of these 2 coordinates. And because of the requirement of special conformal transformation invariance, and it can only take this form. So in general quantum field theory, which not without conformal invariance, it's very hard to pin down the specific form of it. But in conformal field theory, it has only this option that it must be like this. And after normalization, the same 1-2 coefficient actually can drop out. So it's just like this one. Okay, I'll just set it aside, and I'll move on to talking about the supersymmetry here. Supersymmetry actually is a quite important theory in theoretic physics, proposed by Sidney Coleman and Jeffrey Bandula in 1967. We say that, well, just stay like this one. So dimension greater than 2 and longitudinal scattering quantum field theory can only have symmetry group as a direct product of Poincare symmetry and internal symmetry. Like Poincare symmetry is a space-time transformation that we all have. This is like a must, like a imperative in constructing quantum field theory. And internal symmetry in standard model will have SU3, fluid symmetry, SU3, color symmetry, and SU2 for electrical field theory. So these are classified like internal symmetry. You can't go beyond this, otherwise it won't give you some interesting result, because trivial scattering means you don't have any expression at all. But we want to find some way to bypass this theorem. So naturally, for 2-dimensional system, it doesn't constrain by this because it's 2-dimensional. And this is and also for the local at free series, because we don't need to consider the interactions between them. And for the local theory, like in string theory, we have a cosmic string. It's a local because So it's not very feasible, but we won't talk about them here. But set T, which is conformal, because for conformal means it doesn't have a mass, it doesn't have a scale. It doesn't have a scale, so you can't define an ace matrix for a series that doesn't have a scale. So conformal field theory actually doesn't have to comply with this one. And Susie, this is supersymmetry. This theory specifically refers to the case where only the commutator, which is a Lie algebra, is valid, but supersymmetry extended by including some phenomenon generator, and it's an upgrade to greater Lie algebra, so that doesn't have to comply with it. And there's a reason why we have to put forward supersymmetry by introducing those phenomenon generators, and it has a anti-commutation relation like this. And it's formed a gradient Lie algebra, it's an extension of the algebra because it has some sort of phenomenon generators and anti-commutators. I'm going to mention two very important features of supersymmetry. The first one is it has R symmetry, which means this supercharge actually form a multiplet, and after rotating this multiplet, this theory will be invariant. So this is what R symmetry actually means. For SU4, for n equals 4, supersymmetry means it has 4Q and 4Q bar in n equals 4. This is the degree of supersymmetry. Its R symmetry group is SU4 because those Q actually is wired spinous in this case, and the fundamental representation of SU4 actually is a rotation. It's a rotation matrix acting on this four component multiplet. And the second feature is it has PPS backed, because if you I just take n equals 2 as an example, and the same actually applies to all after linearizing the phenomenon generators in this way, and you can calculate, after calculation you find this anti-commutator will be like this. So if you want this series to be unitary, or if you want all the states to be in the unitary representation, which means all the norm will be greater than 0, greater or equal to 0, that is semi-definite. We have to require this anti-commutator to be greater than 0, because otherwise the inner product of the same state will have negative form, which is unphysical. So we have to require these to be greater than 0, by which we have this constraint, and it's greater than the central charge of this theory. Those two things will be important in the following discussions, especially this one. And after learning the conformal field theory and supersymmetry, we actually have a superconformal thing, because superconformal field theory is actually a theory both conformal invariant and supersymmetric. So we have all the generators for conformal field theory and all the generators for supersymmetry. Q is the supercharges dividing like this, and R is generators of R symmetry. And because of K doesn't commute with Q, it gives you some new phenomenon generators, which we denote as S. So for superconformal algebra, it has these generators. Oh, and if you have any problems during my talk, please interrupt me directly. I'll try to answer them. Our talk will be focusing on n equals 4 super mu's, as you see from the definition of the ASFT correspondence. So for this theory, it has SU224 as its superconformal group. What does it mean? Actually, this SU4, this 4 stands for SU4R symmetry because n equals 4. Okay? And this SU22 is isomorphic to SU24, which is a conformal group. So all of these have been sort of taken into account in the past 5 minutes, and I'm sure, well, this is the SU24 and this is R symmetry. Okay, so we have a new location here for superconformal field theory. And it has 32 supercharges because it has 4Q and 4S. For each Q, it has two, because it's a wide spline, it has two components, and each component is complex. So Q gives you like 60 supercharges and S gives 60 supercharges, and combining both, you have 32 supercharges in this theory. And then we move on to talk about super mu's, n equals 4 super mu's. Generally, you can write down action just quite simply because it's a supersymmetric theory. And we'll just talk about n equals 4 aligned force. After dimensional reduction, we reduce the 6 dimensions and we get the 4-dimensional n equals 4 super mu's. How this is done is, to start with, you write down the action for n equals 1 super mu's. Because it's n equals 1, and this gauge theory must have a gauge field. So you must have a spin 1 field. Spin 1 field, the kinetic term for the spin-wide field is going to tell this. This is like the standard, right? And it's n equals 1. And after acting on the vector field, you get spin one-half field, one-half field, which is this one. So this is a general fermion notation. And this is like a kinetic term for the fermion theory. So this is spin 1, spin 1/2 because of n equals 1 symmetry. This is something you have to understand after learning about symmetry. And this -2 is a normalization factor here because of the trace, where you define the trace of the generators of theory to be TRT equals like 1/2 delta AB. Doesn't matter. And anyway, you can do is a Kazuta-Klein dimensional reduction by putting this one here and substituting all this back in this equation, get this action for super young news and equals for super young news. You don't need to bother with the specific form of it, but I want to make it absolutely clear that this action, you can see the coupling constant here, denoted as G. It is super conformal. It is conformal because the coupling doesn't run with scale. Because in quantum field, like in QCD, you have something called asymptotic freedom, which means in like smaller energies, smaller distance, the coupling for QCD actually gets smaller, right? But in this one, because it's conformal, it doesn't have any energy scale. This G will be like invariant under the running along the direction of the energy scale, which means the beta function of this is actually equals to 0. So this is something I want to stress. And also you have 6 scalar here because you have 6 scalar corresponding to the 6 reduced dimensions. 6 scalars and also 4 fermions. And 6 scalar actually transform under SO6, which is locally isomorphic to SU4. So again, this action has this action, A is supposed to be has SU4 as its symmetry group as we talked about in the past. So it doesn't have a running coupling constant and it has SU4 as its symmetry group. This is what I want to say by sort of typing down this thing here. Then after talking about gauge theory, we move on to the other side of the correspondence, which is squarity. So this ADS, CFT, we've done CFT, then we move on to ADS. And this space is actually an embedded space in R to D-1 space-time. And it is sort of it's like a hypersurface, like a sphere in 3-dimensional space. We have R squared equals X squared plus Y squared and Z squared, right? So in this, it's actually the same, but it's not the same. It's actually the analog of Lobachevsky space-time in 3-dimensional. And the metric can be written like this. So I'll talk about this later. Another coordinate transformation, you can write the metric in this form. And you can identify this T, dTn squared and dxi squared. So this one is actually Prongahit metric, probably, as you notice, minus 2t squared plus dxi. So this has Prongahit symmetry group. Has a Prongahit group. Symmetry group under Prongahit transformation as this subgroup, which is SO1D, S1D minus 1. It doesn't matter for ADS5, it has SO13 as its subgroup. And also, this is also invariant under dilation. And dilation group is SO11. So it has symmetry group SO13 and also SO11. And the direct product of those terms will give you SO2D. And also, another way to think about this is for a 2-sphere in 3-dimensional space. It is actually invariant under SO3 because it's only in 3-dimensional rotation. So a sphere in 3-dimensional space will be invariant. And also, this is like a direct analog. It's R3, a sphere will be SO3. So in R2D1, this will be SO2D. So like a direct analog. You have 2 ways to think about it. And also, another important thing about this space is actually a solution to the Einstein field equation without energy tensor. Energy momentum tensor doesn't matter. We have to add a cosmological constant here. So this equation will get this metric. This metric doesn't, well, depends on the coordinate you choose naturally. And by solving this, you can calculate the Ricci scalar. I'm sure you've taken general relativity course, right? So Ricci scalar, and also you can contract both sides with eta, with metric, and you can get the relation between those two. By calculating this, you get this one. And substituting d equals 5, we get actually for this space, it has constant active cosmological constant elective curvature. Okay, this is like an important feature of it. And another thing about it is, after another coordinate transformation, we get to see that for a signal, and it's basically the light, and it travels along the large geodesic, which means this equals 0, and along a water direction with constant dxi, so this will be 0. And put it back to this side, we do the calculation, we get to see that for a light or signal to go from the center, basically the inner part of it, to the boundary, will only take finite time, because this is actually convergent. So, which means that there's a possibility for the signal inside this space to transmit to the boundary of it, which would be quite important to understand the holographic principle, which means the boundary of the space-time would have all the information needed to describe the whole system. Because they do have the possibility of connecting those two regions, because it only takes finite time for light signal to reach the boundary. And then we have another form of the metric. Well, don't bother with mathematical details, it's not important. And you can see the boundary actually lies as R approaches 1 because it has singularity here. And so, which means that any space is actually non-compact, you can never get to the boundary, not as if you travel at the speed of light. And there's a different form of the metric, you actually find that when at the boundary, this metric will reduce to the general cosmic space-time metric. And which means the boundary of it is 5 would be isomorphic to R crosses 3. This is isomorphic to R 3. So which means the boundary of it is 5 is an equidistant space, like the one we actually live in. And then talking about type 2 superstring for a while. The superstring theory lives in 10-dimensional space-time because otherwise it has contradicted. We will have contradictions against the Lorentz invariance. We must have Lorentz invariance for every known field series, so this is like an imperative as well. And it has two sectors, and it has two sectors. I won't go into details, we can ask a question later, but it takes too much time to explain it here. And for Dirac spinors are actually 2 to the power d divided by 2 components in d dimensions. Because they must satisfy Clifford algebra, that is the anti-commutative gamma mu equals 2 to mu mu. And in 10 dimensions time, we must satisfy that relation as well. So you need like rank 32 matrix to represent the Dirac fermion, to represent this fermentation. Okay? So, which means you have 32 components Dirac spinors in 10-dimensional space-time. But in 10-dimensional space-time, we can impose the reality condition, which means it must be Majorora. It can be Majorora, and at the same time, the chirality condition can be wild at the same time. So for a Majorora wild spinors in these dimensions, the components of Dirac spinors will be reduced by half and by half, because this reduced by half and this reduced by half, which gives you 60 supercharges for each sector. And you have 2 supersectors, so you have 32 supercharges in total. This is the reason why it's called type 2b. It's type 2 because it has n equals 2 supersymmetry. This is n equals 1, this is n equals 1, until n equals 2, so it's type 2. And type 1, you probably know that strings have 5 types. Type 1, any type n equals 1, so it has 16 supercharges. So this will be important. Remember, we talked about this before. For n equals 4 super mu's, it has 32 supercharges actually in match. So that will be important. And deep ray, this is something you have in string theory, because for open strings, you must have this endpoint on the deep rays. So we'll be interested in the D3 ray case, because D3 ray means it has 3 spatial dimensions, and plus 1 temporal dimensions will give you the linguistic space we live in. So this will be important for 4-dimensional supermuous theory, because 4-dimensional theory live on a place which is a deep ray containing 3 spatial dimensions and 1 time dimension. And you can calculate the open string mass spectrum in this way. And this is like the oscillation mode. And it must be like this one. So for this ray, it has 10 dimensions, and the 2 dimensions will be on the deep ray, will be transverse to the deep ray, and the rest will be perpendicular to the deep ray, which is only scalars because it has like 6 components, and this has 2 components. Remind you that the photon in our space-time has only 2 degrees of freedom. This 2, 3 means this is actually a vector. It's a vector, it corresponds to a vector field on a discrete ray. So for a single DP ray, you have a vector field on it because you have a vector here and have the same degree as photon. And if we consider n discrete ray, we have a mass spectrum like this. This is like the interval between two deep ray. If they coincident, which means this equals 0 because it just bumping each other, there won't be any space between them. And you get to see actually it contains SUM gauge field. Because I don't know how to say this. You have a deep ray, you have a string start and end on it. You have two, you have string 1 start and end on it, and string 2 and start and end on this one. And also two strings start from ring 1 and on ring 2, and start from ring 2 and on ring 1. So you have 4 possibilities. So for n string, n brings, n deep brings, you have like 2 to the n, right, 2 to the n possibilities there. And which is actually n to the power 2, that is n squared. Right, for n equals 2, this is 2 ring case, you have 4 possibilities. For n deep ray, you have n squared possibilities, which is exactly the number of the generators for UN group. Sorry, for UN group. And UN group actually is equal to U1 plus SUN. So we can drop the U1 factor because it only changes the phase. So which means you have SUN gauge field and coincidence deep rays. This is what you can say when we talk about 4-dimensional superharmonious with gauge group SUN. So probably this gauge field will live on this deep ray, okay? Over these deep rays, not these. And after talking about all the foundations really to understand this correspondence, we'll move on to why Hamada Sela proposes in 1997. Some motivations will be provided here. And I have two arguments here. The first is the symmetry. We have seen that in conformal field theory, it has conformal group SU24, our symmetry group SU4. Combining both, we get SU224, right? And for ADS5, we have conformal group. This is the isometry group for ADS5, and for ACE5, this is a 5-sphere in 6-dimensional space-time. Actually, it's invariant under the rotation in 6 dimensions, so it's SO6. And SO6 is isomorphic to SU4 locally. So you can see the global symmetry and our symmetry match on both sides. And they both have astrality. And the first, well, it's like a special linear transformation. It's a fraction linear transformation containing only integers as its transformation parameters. It doesn't, well, anyway, they match as well. And the supercharges, both series have 32 supercharges. So from the symmetry side, we have the same similar amount of supercharges and the same symmetry group. This just tells us probably these two things are the same. Okay? And the second argument is a decoupling argument. We consider two limits. When the string coupling, which categorizes the interaction squares of the strings, is incredibly small, approaches to 0, we'll get a 4-dimensional SUN gauge field, that's what we mentioned, because you have a 4-dimensional SUN gauge field living on this n coincident discrete rays. This thing appeared like 3 slides ago. And when the string coupling is great, it's really greater than 1. It's much greater, much more greater than 1. This discrete ray would have a gravitational effect, which means it will curve the space beside it, okay, beside it. And it can be seen as a solution to 10-dimensional supergravity. You can write down action for this 10-dimensional supergravity like a really different unarguable one containing like Chen-Simon stone and all the large product. But you can solve it like containing the like the 5-form and the Paladin field and the scalar field there. You can solve for it metric of this discrete brain curving space directly, and you get the result like this one. And by taking the limit r approaches 0, which is when we go towards these brains, we'll get a metric like this, because this one will be left out. And then do a coordinate transformation. We're going to see this is nothing but the same metric for ADS5 and cross S5. So by looking towards these three branes, and you get the same metric as it is 5 cosine phi. So when the coupling is really weak, it gives you a few each field. When the coupling is strong, it gives you a 5 cross 5 space-time. And when looking far away, in the first case, the gravitational effect of the D brane will be ignored, can be ignored. So in far away, it has nothing but like a flat space-time, it's a 10-dimensional space-time, 10-dimensional supergravity. And for this metric, when R approaches infinity, this will be 0. This will be 0. It's reduced to a flat 10-dimensional space-time. So in both cases, what remains at far away is free 10-dimensional supergravity, which means when the coupling is weak, this thing decouples as 4-dimensional Williams and 10-dimensional free supergravity. And when the coupling is strong, it decouples as 8s5 times s5 due to the gravitational effect and also the 10-dimensional supergravity. So since both descriptions are definable, because for no matter for whatever value GS takes, those two things actually are definable, are both valid descriptions. We just assume that they are the same. This is like a direct motivation for this correspondence. So actually, I provide you with two motivations. The first one, the symmetry group, which we have told so much to find, and also the second one, the coupling argument. Both motivations just need us to believe that these two things actually are the same thing. And this segues uniquely to this very important thing in theoretical physics, and also improve our philosophical understanding. Just think about taking pictures. You have a 3-dimensional object. You take a picture. The photos will be like 2-dimensional, but using 2-dimensional photos, you can actually have all the information you need to describe the 3-dimensional object, right? So this is what we mean by saying this is what holographic principle means. Just think about a black hole. The black hole is like an object in space-time, and Hawking and Bekenstein proved that the entropy of it can be written like this. So it's proportional to the area. This is known as area law in black hole thermodynamics. So the physics of the black hole can be described by area. So the information you need is actually contained in a lower dimensional space. And also in this case, talking about this correspondence, we have said that the boundary AS5 is actually R13, which is a 4-dimensional space-time. And this 4-dimensional space-time has a 4-dimensional superambiguous, which encodes the information of this AS space-time, because these two actually are equal. So we can use a like 4-dimensional gauge theory to describe a gravity theory in high dimensions. So this is what we call like holographic principles of what can be described by its boundary. And this has some rather profound philosophical implications in our understanding towards the universe. And these are the final checks of it, but due to the time and the wise, I won't do it here. Just that you have standard way to calculate the endpoint correlators in quantum field theory. And this is generally functional. If you learn about Pass integral, you understand why it's written like this. And also, because of this correspondence, we can use the action in supergravity to calculate the generally functional for the gauge theory. And after some calculations, you can have the same result. This is the result we obtain by adopting this supergraph, that is an action of supergravity. And it has the same form as those the way we proved at the very start of my talk, at the same form. And another check is black hole entropy. This is fascinating because entropy, the black hole has entropy, actually it has microstate, but in classical theory, you don't have some inner degrees of freedom black holes. And you can count this this degrees of freedom by using gauge theory. Because we have bigger states, I mentioned that in talking of supersymmetry, and black hole can be against black hole because so star you can't have an exposed similarity, which means M must satisfy, well, there will be a lower bound of M. And it has to be BPS because the supergravity describing it has some supersymmetry. So this is what we call BPS black holes. And okay, anyway, you can calculate BPS states in your gauge series by using superconforming index. It's defined in this way. Generally, because BPS states has this equals to 1, has this having this equal to 1, and all those generators commute with this. So for BPS state in super news, those two things, this field and its super partner will cancel each other because they have a different -1f. So the law contributes, the new state contribute will be BPS state. And you can use this to count BPS state, and after calculation, you use some method to calculate it, get this result, and this plugging back this definition of entropy from the gauge theory side, you can get the same result as what you obtain from the gravity side. This is what we have as proof of this correspondence. And this will be my talk. So, do you have any questions?
大家也可以用中文提问啊，中文就问一些问题，大家自己问一下。问问题。
Yeah, I think I made this too long, so you don't have any problems at all.
这个你这个理论的话，能不能跟标准模型联系起来？
可以，因为这个可以算 QGP， 就是那个 QC 里面它有强耦合的话，强耦合因为它是不能用对偶律去做的嘛。然后这个对偶的话，它是强弱对偶，就是说我对标准模型就强度这边的强耦合的这个区域，它对应的是在引力那边的弱的区域，就是 supergravity。那个 supergravity 的作用量我们可以写出来，所以我可以用那个来算，就是在这个规范里面这边的强耦合，比如说像高开张子比例体，在 QC 里面没法解，就是这个可以和标准模型联系。
那它从理论一言出标准模型，你假如你是一个上层的理想好，一言出一能的这个标准模型 SU3、SU2、一能的标准，能不能理解？
这个我觉得应该是用弦论去研究的东西，不是应该用对偶来。
对，我是说就是弦论能不能一言？
做不到，就是做不到这么完全，因为弦论它的激发态，它的就是它给出那个标准模型，比如说电子质量、质子质量，它没法用那个质量谱算出来，就是它的那个，就算你把那个阿尔法派随便取，但你给不出标准模型那些例子，它的规范群它也没法给出来。就是我们考虑 intersection brains in string theory， 它做这个交了以后，它也没法这么完美的表出标准模型，但它可以给出，比如说基带的那个比如说基带的亲子，可以给出来，可以做到那个。
还有就是你现在大三哈，学这些大爱，学这些知识，你自己感觉比如哪些知识点是你觉得是最难的，然后哪些知识点是让你最激动的，能不能给大家分享一下？
知识点最难的话，我觉得可能，比方就是这个supergravity， 就是你看它作用量基本上很复杂的一个，你没法去解释它每一项是什么东西。然后还有就是量子反常，量子反常是就是我们很多理论的构造，比如说你超引力，它去引这个transistor，就为了克服量子反常。但是这个怎么克服的这些过程，就是对我来讲还是很未知的。那包括像这个 superconforming index， 它有很多计算方法，比如说你可以用贝塔 ansatz， 还有就是用安点去计算，这个东西我也不知道它怎么算，总而言之就是会有很多问题了。然后这是我觉得比较难学的，但是基本的课，比如说像是就学校教的课，就应该不算特别困难，对吧？然后我觉得比较激动的点就是，比如说，你看哈，这个爱因斯坦的这个广义相对论，他觉得这个引力效应就是它是一种几何效应，我觉得这是一个非常漂亮的事情。还有就是，比方像这个对偶，你想啊，一个引力理论和一个规范理论，就一个东西完全没有引力这个效应，然后你可以讲的全是引力，它两个之间将有这样深层的联系。所以你看这个事情，所以我的标题叫 physics dilemma， 对吧？就觉得它这个是个非常 attractive 的一件事情，拼命的一件事情。我觉得这是我学物理比较激动的。
这个理论对一些新的一些实验观测，比如中微子质量问题，或者是那个中子的 CP 破坏问题，它有没有什么解释？
没有办法，因为你要解决你的那个，比如说 CP 破坏，CP 破坏，它能量应该是统一的，是吧？对吧？它对，那你对应的就是那个，刚我说它有个强弱对偶的问题，那它对应的是那个 gravity side 就是弦论对面的高能标，高能标就不是用 supergravity 做近似了，它用的是弦论，但是弦论的样子它现在做不到，就是我们可以写出那个 supergravity 的作量，但是弦论我们没法知道，因为它的能量太高了。如果说它真的有这种联系的话，你得用高能标的弦论去解释你讲的那个 CPU violation 或者是中位质量的吧，这个做不到，因为你那边你做这个对偶就是为了解决问题的，结果你那边那个你根本不知道，反正你这个conservative regime in standard model 或者 in gauge series 上你还是很清楚的，所以它做不到这些。